Okay, let me see if I get this. Got to reset my mouse here, and we will get started. Okay, I'm Bill Snyder with the Gustav Larson Company, and today we're going to talk functional overview and how to troubleshoot Mitsubishi. We'll try to go pretty fast here. Save your questions to the end. First of all, how we attempt to do things. A normal compressor just starts and stops. What we're showing here on this chart here is this is kind of a timeline from left to right. And if it was 80 degrees in the space and we turned the thermostat on to a set point of 74, the compressor or contactor will pull in and will run for a period of time until the thermostat is satisfied. So we kind of get this type of system with a conventional system where the thermostat comes on, it pulls in the contactor, the ampere on the compressor will typically spike, and we'll continue to run the contactor and compressor until we meet the set point on a conventional thermostat. It opens up, drops out the compressor, and we'll coast for a while until we raise the temperature above set point, and we kind of get this on-off contactor compressor running on-off, and the temperature, although this is kind of exaggerated, between 72 and 76, not uncommon to fluctuate 1 degree above and below the line, just trying to maintain a set point. As long as this contactor is pulled in and the compressor's on, the evaporator should be cold and below the dew point and drawing humidity out of the air, which in some of our areas is extremely desirable to keep the humidity low. And that's the way a conventional system works. Now, with the Mitsubishi inverter, we're not limited to 60 hertz. We can go all the way up to actually about 125, 130 hertz at times, depending upon the equipment. So in the same scenario, we actually, if this is a timeline, we can actually pull it down colder faster because we're ramping that compressor way up. And I'll show you how we do that as we progress. But we start out very slow like this. We start out very slow and then we ramp it up. So if you would put an amp probe on this, you're going to find that you don't have that huge spike right when the contactor pulls in because of the way we do it. So it drops the temperature a lot faster. We have thermistors that are sensing that we're getting closer and closer to set point, and that we're about to achieve the set point. So it's going to back off on the compressor and slow it down. This kind of acts like your car does when you put it in cruise control. As you go up the hill, your gas pedal goes down, and as you go over the top of the hill and start coasting down, your gas pedal comes up. Kind of the way we work here. We slow the compressor down, we speed it up a little bit, we slow it down. But you'll notice there's no off cycles. Typically, on a warm day, this compressor will run all day long, but instead of running at 60 hertz, we're slowing that down to, in this case, around 30 hertz. Conserving energy, yet keeping a cold coil, which is helping to dehumidify and making the space more comfortable. Okay, so how do we do this? This is a hyperheat system that we're looking at. We'll go into more detail on the wiring and the piping a little bit later today, but this is the compressor here. And this particular unit, because this is the indoor unit, this is in the heat mode. So the indoor unit becomes the condenser. So this hot gas coming off the compressor comes up through the reversing valve and right to the indoor unit. So we're in heat mode. First thing you see here is this little black dot here is a discharge temperature thermistor because we're monitoring the discharge temperature coming off that compressor. There's a high pressure switch and charging plug in there. We go through the reversing valve. You'll notice there's a strainer here. Mitsubishi has lots of strainers that they have in their equipment. So just be aware that there's strainers there that will pick up any junk that might be in the system. They could plug if there's a lot of stuff in the system. This dotted line here represents the difference between the leaving the condensing unit and going towards the indoor unit. So this ball valve here is actually your service valve, and this ball valve is your service valve. So you've got two service valves. Typically, you have a liquid and a suction. We actually have a saturated liquid line and a suction line, and we'll explain how that works as we go through here. So we go through, this is your line set to the indoor unit. You have an entering coil temp, condenser evaporator temperature, that's the entering coil temperature. We have a room temperature thermistor, that's a return air thermistor, measuring the return air temperature. And we have a leaving coil temperature. So we have the superheated vapor going through and getting cooled off through this condensing coil, which is now inside coil, heating the home. We leave there with subcooled liquid back through the service valve on the outdoor unit. There's another strainer, an LEV, which stands for linear expansion valve. It's an electronic expansion valve is what that is. And then another strainer, both sides of this. So no matter which direction the refrigerant's flowing, we're going to pick up something and try to protect. If there's anything in the line, we're going to pick it up at the strainer and try to protect the LEV. When we come out of this LEV, we're now in a liquid vapor mixture, and we go through this hybrid accumulator, because you'll see this line dips into the accumulator, and the suction line, this blue line, is also going through there. We come out of the accumulator through another strainer, and we go straight through here through an LEV to the outdoor unit, which is now an evaporator. And we change from the subcooled liquid to a saturated liquid, go through another strainer, an outdoor entering coil pipe thermistor, and a leaving coil pipe thermistor, and an outdoor ambient temperature sensor, which is a thermistor, through the reversing valve, through the accumulator, through another strainer, a low pressure switch, a suction temperature thermistor, and into the compressor. Now this is a hyperheat unit, so we're doing some other fancy stuff here. We're trying to capture as much heat off that gas, so we're running through another LEV here, and we're going through a tube-in-tube heat exchanger, and we are cooling this liquid, subcooled liquid, to the outdoor unit, and we have a kind of a liquid vapor mixture that we're injecting into the compressor. So we're injecting some liquid vapor mixture in here. We're ramping that compressor. Remember I said up to maybe as high as 130 Hertz. So that compressor is running really, really super hot and pumping a lot of hot gas into the indoor unit. This thermistor is talking to the onboard computer, which is a little circuit board, and telling it what's going on and saying, hey, I'm getting really hot. Either I have to slow down or I have to feed a little bit more liquid vapor mixture to cool it off, and it makes all these decisions. So that's kind of how it works. That's the fast way of explaining it. Now, I don't know if you all know what hyperheat is. We'll talk in a little bit more detail on that in just a minute. But hyperheat will allow you to heat and get a lot more heat out of the system and run at a lot lower ambient than a typical heat pump would. So, okay, now we'll talk about the inverter circuit and how that works. This over here is a sine wave, and this is a sine wave. And when we talk about 60 cycles or 60 Hertz, Hertz is the guy that came up with this. 60 cycles is that over the center line, we alternate the current above and below that line. That's why we call it alternating current. And we do that 60 times a second. So when we see on our diagrams this symbol, we're putting AC power in here. And we're typically going in over here on this side with 208, 230, whatever our power is going into the system. So we're putting 208, 230 volts in to this converter circuit, and all of our units work this way. Some of them have one board, some of them have two, some of them have three boards, but they all have these three types of circuits in them. And we'll explain that as we go forward. But just so you know, they all work the same way. This is just kind of a simplified drawing to get us started. These little symbols right here are actually diodes, or a bridge rectifier. A diode actually works very similar to a check valve. If you're familiar with check valves, it'll only let a liquid run in one direction. And these diodes will only allow the electricity to run in one direction. So we've got two separate lines coming in here, and we've got the power going plus and minus. So it will not allow it to run in the minus direction, only in the plus direction up here. So we come out of this circuit here, right here and here, with a kind of a choppy DC signal. Now, if you put a meter on it at that point, you would probably not see it being choppy, because remember, this is 60 cycles between here and here a second. So this is almost doubling that. So we've now gone to like 120 cycles. So on your meter, you'd never see that. You just trust me, it's a little bit of a choppy signal coming out of here. So then we go into a smoothing circuit. In the smoothing circuit, we see this little device here, kind of looks like a transformer, but it's just a big coil and a big heavy magnetic field. And we run the electricity through there. It's called a reactor, or noise, part of the noise filter. Then we go to these devices here. Now what these are capacitors. They're smoothing capacitors. And they actually smooth the circuit out a lot. The way a capacitor works is as you apply power to it, it absorbs the energy, and when you start to remove power away, it discharges. So what we do is, as the power goes up a little bit, we're absorbing, and then we're discharging. So it's taking this signal here and making it a very, very flat signal. It's a very good DC signal. So then we're coming out of here with DC voltage. And typically that voltage is around 300 volts DC. And if you really want to calculate it, is you take your input here, you take your square root of 2, and the square root of 2 is 1.414 and a bunch of digits behind it. But if you take 1.414 times whatever that electricity is coming in here, it'll pretty much give you what your DC voltage is coming out. So if you've got 212 volts going in, you will have 300 volts coming out. If you got 208, you've got 294. If you're at 230, we'll be at 325. To give you an idea, we always refer to this as around 300 volts. It's not going to be exactly 300 volts, but a lot of the slides we show you 300. The only time it's going to be 300 volts is if you got 212 volts steady coming in. Then we go into this inverter circuit. So we take 300 volts into this inverter circuit, and we go through these, they call them insulated gate bipolar transistors, or IGBTs. They're gates or like a triac, if you're familiar with those. And there's a set here, here, and here. There's 3 sets of these, or 6 of them in there. And we're taking this DC voltage and we're running it through these. And what we're doing is we are simulating AC voltage when we come out of it. And it is it's called a sinusoidal 3-phase pulse width modulation, or pulse amplitude modulation, that we put out of here. So we're putting out 3 AC signals out of here, simulated AC signals. And they go to the compressor, and they're labeled U, V, and W. So if you had 3 electrical lines going to a compressor, you would typically think that's a 3-phase compressor. And basically is a three-phase compressor the way it's wired. The signal going to it is, we're varying the voltage now and the sine wave or the frequency. So it's no longer going to be 60 hertz or 60 cycles. It's going to be something other than 60, depending upon how fast we want that compressor to run, and the voltage will vary. When we do that, it doesn't overheat. If you just put a resistor in the line, the windings would overheat and we burn up the compressor. When we're chopping the sine wave, we're able to run that compressor really cool, really efficient at a very slow speed or very fast speed. It's very, very efficient. These little things here are almost like coils. Think of these as like an amp probe. We're monitoring on the main board what the amps are basically going to that compressor. So we can tell if the compressor is any two windings. We can see if the compressor is running properly, if it's overheating, if it's running high amperage or whatever. We will slow the compressor down, or we will shut it off and throw an error code. We're always trying to protect the equipment. And if you take that compressor and you measure across U, V, and W, you should get very, very similar voltages. It should not be more than 10% variance between U and V, U and W and V. Just like you would ohm out a three-phase compressor or check the voltage going to a three-phase compressor. We would do it the same way. I always say there's a difference here because we're varying the speed of the compressor, and when I'm checking out a compressor, if I'm not in test mode, I'm always listening to hear a pitch change. If you hear a pitch change, the compressor just slowed down or sped up. And if it's slowing down or speeding up, you're going to see these voltages change. So when you're doing these checking, you're going to check them fairly fast and listen to make sure that it's not changing voltage or changing the speed. Okay, I'm going to go right past these things and keep talking about the slides because we're kind of limited on our time today. When you're checking the voltages and the way the indoor unit or outdoor units work, we're checking between S1, S2, and S3. And there's also a ground here. S1 and S2 are line voltage, and we'll just drop our meter across there like they're showing in the diagram here. And in this case, we're reading 210 volts. Between 2 and 3, though, is a pulsing DC voltage. And depending upon what type of meter you have, they react differently. So if you have one that's working fine, I would suggest you take your meter out there and see what type of voltage, DC voltage you're seeing between 2 and 3, and just see how your meter works. This top analog meter, I'm old enough that I have an analog meter, and it actually reads this DC pulsing voltage the best. The needle bounces up and floats around, and you can see what's happening. This type of meter, there's a scale on the bottom. You can see 0 through 40 here. That's the analog scale, and that'll kind of bounce around. And if it's bouncing around, that's a good thing. And on the fluke meter, by the way, you won't read on this meter here, this type meter here. When you look at the voltage, this thing will bounce so fast you can't tell what's happening, but you can tell what's happening on the scale on the bottom. On the fluke meter is actually a very, very fast meter, and you can actually see the voltages. It'll say like 12 volts, 25 volts, it'll bounce around. And then it's also got a scale on the bottom, but that thing is, it reads a little funky the way it bounces around on there. So I say you might want to grab a meter and just check one that you know is working fine, just to see what a good signal looks like. So when you get out and you check these, you'll just know. Okay, let's look at a PUZ. This unit kind of looks like this. This is a P series. It's a professional series. This one actually has 3 boards in it. And we come in here at the bottom on L1 and L2, and we go in and we hit the this is the, it says NF, this is a noise filter board. We come through that board, and these wiring diagrams will not be, they'll be clearer in the books that come with the service manuals that you can get online at mylinkdrive.com, but they will not be color coded. They're color coded here to hopefully show up on your screen a little bit better. In this case, the blue is 220 volts, an AC circuit. This yellow line is the DC signal to S3, and the red line is your DC 300 volts DC circuit. So we come through with L1 and L2, we come through the noise filter board. We come out of the noise filter board up to this main PC board. You'll notice there's two fuses here, F1 and F2. And then we come back to S1 and S2. So essentially, L1 and L2 power coming in should be what you read on S1 and S2. In some of these diagrams, you'll see it literally goes immediately from L1 to S1, L2 to S2. But the odd thing here is we're using S2 for power, and we're also using it as a common signal for the S3, which is a DC signal, DC pulsing signal. So you can't mix these up. S1 on the outdoor head or outdoor unit has to go to S1 on the indoor head, and S2 to S2 and S3 to S3. You can't mix them up. It's not like L1 and L2, you can mix them up, doesn't make any difference. On this, it does make a difference. So just be careful with that. So anyway, we come through the noise filter board, we come in here, and we go over here to where we convert right here from the AC voltage to the DC voltage. You'll notice, you really can't see it too well, but there's a little wavy signal on the input side that looks like this, an AC signal, and leaving it, there's a little minus and a plus there. I don't know if you can see that. That's meaning that we're on the DC voltage side. So we come out of here, we're coming out of here with about 300 volts DC. And in this case, we're also cleaning this up right here. This is one of those reactors. So we're running the DC voltage through the reactor. Sometimes we do the AC, sometimes we do the DC. In this case, these are little reactors here. So we've got reactors on both sides of this. For some reason, they felt they had to clean up that DC signal. The engineers did. So we come through this DC signal and we go right here to the, am I trying to think, IPM, Intelligent Power Module is what they call it right here. This is the IPM. And that's the same thing as the gate bipolar transistors we talked about. So that's taking the power, you can see a minus and a plus there, hopefully coming in on the red side, and we come out with AC voltage and we go to U, V, and W to the MC, which stands for motor compressor. You'll also see that there's, I don't know if you can see it, there's a little 3 and a wavy line behind it, meaning that this is 3-phase. You have a wavy line like that. So that's a 3-phase compressor. The DC voltage also comes to this, it says CNDC pink. Hopefully you can see that. It's a pink, it's kind of a hot pink connector that's on the board. And they use the same pink connector on all of our equipment across the board. So anytime you see that, it's a indication that that's the 300 volt DC signal. CN just stands for connector. You'll see that throughout Mitsubishi's terminology. CN is connector, and DC just means that it's a digital current coming out of there. This connector has got 3 pins on it, pins 1, 2, and 3. We're only using pins 1 and 3. We leave, anytime you see that 300 volts DC, we try to separate that power because it can arc. So they leave a little space between them. Okay, so that comes up here and goes into the CNDC on the main uh, circuit board or PC board. And again, we're separating it there as well. And then we're going out to these motor. Let's see if I can blow that up for you. Come on, right there. It says MF. MF may not be what you're thinking. It means motor fan in Mitsubishi speak. And there's motor fan 1, motor fan 2, and that's these condenser fan motors down here. But you'll notice it's that red, it comes off of that CNDC and it's that red line. So that voltage is DC voltage. Don't know if you can see it, but on the fan there, let's see if I can hold my hand steady. You got a 3-phase symbol on that fan, but we're running DC voltage to it. What that means is on the motor itself, there's a little circuit board that does this type of, the intelligent power module is built right onto the fan motor. It's inside the fan. And if you were to pull the back off the fan motor, you will see a little circuit board with 3 lines coming out of it to the motor that are labeled U, V, and W. Then there's 3 more lines that come out. And what we're doing is we're sending a DC signal to the motor telling you what speed to run at. And then the motor is sending the signal back telling the board that I'm running at that speed. So it's confirming that the motor is up and running. And if it determines that, hey, I'm telling it to go to so many RPMs and it doesn't get a signal back, it'll send an error code and you will get a phone call to come out and work on the equipment. Also up at the top here, these are thermistors labeled TH, temperature thermistor here. TH, there's a 3, a 6, a 7, and a 32. What this is the outdoor unit. So we have the entering coil thermistor in the outdoor unit, the leaving coil thermistor, the thermistor that's measuring outdoor ambient temperature, and the one that's the discharge temperature on the compressor there. Up here, I don't know if you can see it. Probably not, because it's, hang on. Let's see if I can slide something out of the way here. No, it's not gonna let me, okay. Hopefully you can see it. Maybe it'll show it on another one, but right there is a type of a motor. And there's a symbol that looks like that. That's what we're used to seeing for DC. If you see that symbol, that also means DC. So that little motor there is a linear expansion valve. The way a linear expansion valve works is there's a needle valve in the expansion valve, and there's literally a little motor or rotor on the top. Stator, I guess I would call it, on the top, and it turns that needle valve in and out, and that runs in DC. So anytime you see a symbol that looks like that, it's a DC symbol, and you'll see that throughout the boards. Now I lost my, there we go. Let's see if this thing's working again. Okay. Okay, now this is an MXZ8C48 up here. This thing is the hyperheat model, the one that uses a branch box. This one looks like 3 boards in there. It's got the top board here, the main PC board. This happens to be an MNet board because we communicate on this. And then a main kind of a power board down here. So down here is your L1 and L2. It splits off and goes over through 2 fuses and goes to these B1 and B2. That would be for your branch box. This is the unit that has a branch box, and we can put up to 8 indoor heads on this one outdoor unit. So if you ever find that the indoor branch box is not working, or none of the indoor units are working, but you do have power on L1 and L2, you might want to check those fuses. Otherwise, we run the power out and we go through, this is the noise filter section through here. We take a little bit of the 208, 230 volt, we run up to this board here. It's an MNET board. This is just taking that voltage down. I think it's 29 volts. It comes out, comes over and down through here and runs to, this is the communication line here, right here. This is communication to the indoor branch box. And it's M1, M2 and a shield. Internally, this works the same. We go through here, we go through the IGBT and it converts it from AC volts to DC voltage, about 300 DC. We go through a reactor here to help clean up that voltage. And then we go over here and we go to the inverter circuit and we take that DC voltage and we go back to U, V, and W. It's like a three-phase signal to the compressor that again is labeled as a three-phase compressor, MC for motor compressor. There's that CNDC pink terminal again. It's a 3-pin, but we're only using the 2 outside pins. That little 2 that you see there on the screen, hopefully you can see it. It just means that there's 2 wires that are coming up here. And again, there's a CNDC pink connector up there. And we're doing the same thing. We're going out to the 2 condenser fans, just like before. Series of thermistors up here. This one has 2 of the expansion valves up here. And right in here, we'll talk briefly a little while. These are all your thermistors. And we will talk a little bit about these switches. Most of them you never touch. You could touch SW1, could touch a couple others. We'll talk about an LED 1 and 2. These are segments that we'll talk about that we can use for a number of things on this unit, including troubleshooting. And again, I was telling you, but these are your voltages. And this is 29 volts that comes down from this board here through here all the way down for the communication voltage. And this would be the branch box it goes to. Let me go back here. Over, if you can see this, down in this area, this is where you power the branch box. And on this next screen, this is where that is coming from the outdoor unit to the branch box here. And the communication wires we were showing on the other screen come in here as M1 and M2, and they come in and communicate. That's the 29 volts coming in here. So on this particular branch box, we're powering it up, and we do have a spot where we convert some power here that we're using internally. It's not a 300 volts DC signal at this point, but we're using it to drive these expansion valves, the linear expansion valves over here. We have to set the dip switches. If we've got, in this case, we've got 5, 1, 2, 3, 4, 5 zones or internal air handlers. So we got 5 different expansion valves. Right here is where you turn those on. 1 through 5 would turn on these circuits. They're labeled as A, B, C, D, and E. Over here are thermistors. They're measuring pipe temperatures within the branch box. And then of course, the indoor units will also have thermistors of the entering, the leaving, and the room temperature thermistors on the indoor unit as well. This is where the indoor units get wired up, just like the one-to-one units wire the indoor unit right to S1, S2, and S3. Same thing, S1 and S2 is line voltage, S2 and S3 is a pulsing DC voltage. This is an MUZFH This is this one is a hyperheat. They've now added HZ to the end of the model number here. This is a little old slide, but essentially it's the same unit. Down here is where L1 and L2 comes in. And on this one, you can see it goes right over, don't do anything to it, goes right to S1 and S2. And that S1, S2, and S3 is what goes to the indoor unit. We're coming in here. This is the noise filter section. Up here is the reactor. And here is where we convert it to DC voltage. It's 300 volts DC downstream to this. In this case, we have the IC, which is the power module or inverter circuit. It depends upon where where these boards were designed and made around the world. There was plants around the world. Most of our equipment comes from North America now, but originally it was coming from Japan, a couple different plants in Japan. And I think there was one plant in Taiwan at one time that I don't think is open anymore. I think the tsunami that hit a few years ago, I think they closed that plant. But anyway, depends upon where these were designed as to how some of this stuff was called. This is an IC, which is inverter circuit. It's a power module. It could be labeled IGBT, which is the insulated gate bipolar transistor, or it could be IPM, which is intelligent power module. They're all the same. They're converting from 300 volts DC to the simulated three-phase AC going out to this motor compressor here, which is labeled as three-phase. In this case, we have a circuit here that converts it, and it says U, V, and W, and that is going down to the fan motor on the outdoor unit. So they do it a little different here. We're actually sending three-phase AC directly to this fan motor. And then we've got 5 wires that are your signal wires that would tell that motor what to do and respond and tell it what it's doing. In this case, we also have, these are your thermistors down here. Again, you're entering, you're leaving coil thermistor, your outdoor ambient thermistor, and your discharge thermistor off of your compressor. And this is the linear expansion valve. You can see clearly on this, that symbol, that AC and DC symbol. And you'll see the voltages all pretty much fall into play. Again, this 300 volts is a nominal 300 volts. And obviously your voltage going in is somewhere between 200 and 240 volts. So that's gonna change this. This is a MSZFH. So the MS would mean it's an indoor wall unit heat pump. FH is the unit down here that has the 2 dampers in it. So it's got multiple turning vanes in this one. And this one also has an IC sensor way down. I don't know if you can see it down here at the bottom. Don't know if you can see that or not, because a lot of times you get a black bar across the bottom. But anyway, that's that type of unit. So it's an indoor unit, but even the indoor units have boards is what I wanted to show you. This is the most complicated one. So that's what I'm going to show you. Normally the wiring diagrams have what all the symbols mean on here. Like MF means fan motor. But we're bringing in the S1 and S2 from the outdoor unit or from the branch box in here. There's a fuse. This is the NR over here stands for varistor. That can blow. If that blows, you replace the board. The fuse blows. Sometimes the fuses are soldered on and sometimes they're replaceable. Depends on the board. But the F11 would indicate a fuse. Here's where we convert from AC to DC, and you can see plus and minus. And we go out to the main fan motor here, MS. Is that labeled here? Doesn't say it, but that's the main fan. Down here, you're going to see these are DC motors. There's 4 of them. These are all vane motors. All 5 of these are vane motors. There's some of them are As you'll see, horizontal vane motors and vertical vane motors. These have two flappers that move up and down this way, and then there's vanes that move side to side, internal of the unit. These RTs are your thermistors. In this case, they're labeled RT, and the other diagrams, I think they're TRs, but they're thermistors in here. And this motor right here is the IC sensor motor, I believe. Yeah, IC sensor motor here. That's a little sensor that rotates throughout the room and scans the room and looks at temperatures within the room. And it gives you on this unit the ability to either keep the room at a certain temperature, you can throw air at somebody, or you can throw air away from somebody. So if you have a woman in an office that doesn't like the air blowing on her, you can set it to make sure that it always blows away from her. So if she moves from desk to desk during the day, it'll move and keep the air from blowing at her. If you got a hardworking guy that likes the air blowing at him, you can do that as well. So kind of a neat little system. And these are all just different, the receiver board for the remote controls, and the display board, which is the LEDs, that sort of thing. So, and then this I wanted to show you just because this SEZ is a little air handler. This is the indoor board for the air handler. Again, thermistors, works pretty much the same way, except for this one, instead of a remote control, you actually control, there is they call it a control, but it's a wired control. This one happens to be what they call a simple MA. And there's just two wires that wire up and connect onto the control board. There's just a terminal board here that you would wire your thermostat wire to on this one. Again, this is your your S1 and S2 are your communicating voltage to the outdoor unit, or I mean, sorry, S2 and 3 are communicating the outdoor unit. S1 and S2 is your line voltage. We do have a rectifying circuit in here to go to the fan motor. But what I wanted to show you here is this little box here. This is how, these are your terminals 1 and 2, or 1 and 4, and here we left 2 pins off. This is 300 volts DC between 1 and 4, 4 being the negative side or common. So if you check between 4 and 5, you should read about 15 volts all the time. 6 and 4, you're getting between 0 and 6.5 volts DC, and 7 to 4, terminals 4 to 7, you would be reading somewhere between 0 and 15 volts DC. This is the circuit that sends the speed to the motor, and this is the circuit that responds back and says that I am turning. So it just gives you a little bit of an idea of how that works. This one also has a drain pump or a lift mechanism. It's not really a pump, it literally lifts, because this drain is on the bottom of this, and this could sit against the ceiling. It literally lifts the water out of here and slings it out the side. It doesn't pump it, it just kind of slings it out the side. So you would gravity feed from there. Okay, refrigerant system overview. Moving along pretty quick here. This is very similar to what we looked at this morning or earlier in this session. We've got the compressor here. We come out of the compressor through the reversing valve. In this case, this is going to the outdoor unit, so we're in the air conditioning mode. Again, you can see all the different thermistors on here. There's also an outdoor air thermistor here someplace. Don't know. Oh, that's the ambient thermistor, and then there's an entering and a leaving thermistor. Strainers, LEVs, more strainers. That's that heat exchanger going through to another strainer, another thermistor here, through the stop valve or service valve on the outdoor unit. We leave the outdoor unit and we go to a branch box here. These are all the LEVs. These are all capillary tubes, and these things here are all strainers on this side of it. So see, we got a strainer going in here, a strainer here, a strainer here, and these are all strainers here. We've got an entering coil thermistor, a ambient or return air thermistor, and then there was thermistors in, this would be where we read the leaving coil, which is within, these are thermistors that are within the branch box. And then we go back and we go through another strainer. There's another thermistor here going through this hybrid accumulator and into the compressor. And then of course, this is the circuit that keeps that compressor cool. Okay. Let me move on to this one. This is a PUZ. This is a P series, also a hyperheat. So it's got this circuit. If it's not a hyperheat, it will not have this heat exchanger circuit in here. But again, we have the thermistor measuring the discharge temperature of the compressor. You go through a muffler, through the reversing valve to the outdoor heat exchanger. So we're in the heat mode, or in the cool mode here, because we're dissipating the heat outside. Again, we have an outdoor ambient thermistor, and we have entering and leaving pipe temperature thermistors. There's a thermistor right here and a thermistor right here. Linear expansion valve, strainer, go through that heat exchanger circuit, another strainer. This is the power receiver, because we're running a liquid line through this, plus we have a dip from our suction line. So we're doing some heat transfer here, we're doing heat transfer here, and we're driving this compressor to a high speed so that we get as much heat out of it as possible. That's allowing us to get 75–80% of the unit's capacity at -13. At 5 degrees outside, we're getting 100% capacity out of all these hyperheat units. And then we just go through and complete the circuit back, same as what we've just seen. It's very similar. Now this is a non-hyperheat, just standard unit. We come out of the compressor, we're still monitoring the temperature coming out of the compressor through a muffler. These units are extremely quiet. That's one of the reasons the linear expansion valve is in the outdoor unit, so we don't hear any hissing and all as the refrigerant expands. We expand and start doing that in the pipe going to the indoor unit, so it makes it quiet. So we have mufflers. That's what all of these capillary tubes are. They're getting rid of any pulsations and so forth in the system to try to make it as quiet as could be. There's another capillary tube here. We're actually doing most of the refrigerant control with a linear expansion valve. These are getting rid of some pulses and things that could cause some noise in the indoor unit. So this works very similar. We just don't have that heat exchanger circuit like we did on the hyperheat models. Okay, come on, let's move. There we go. Talk a little bit about troubleshooting. There's a blinking light on the indoor unit, typically if it's a wall unit, that show up like this in the instructions. This is just telling you the blink interval. Pretty easy to tell that it blinks maybe 3 times and a pause, 3 times and a pause. Then we would go to the service fax and get that information. And in there, it will give you a failure mode. And where you would get this is on the mylinkdrive.com. You just type in that in Google and it'll pop up. Don't need any kind of a password to let you right in. You pick the M series. If you're working on M series, you pick the model number of the outdoor unit or the indoor unit, and you'll get this type of a flash code. This is the operation indicator on, I believe, the indoor unit. Yep, it's up here, indoor unit. If it's flashing 1 time, it's telling you that you're some sort of problem with the room temperature thermistor, maybe the coil temperature thermistor, indoor fan motor. It would show up there. It might even refer to you to the outdoor unit, because you can throw a code on the inside that may refer to an outside, but it would tell you that under the conditions and the remedies. That makes it kind of easy. And this is still on the indoor unit. This is the type of fault codes you would see miswiring. If it was just blinking on, off, on, off, on, off, it would be a miswiring signal. This would be a 2 flash, would flash twice, and then there'd be a 2.5 second pause and flash twice. And this is telling you it's a room temperature thermistor. You have to make sure you grab the codes for the correct piece of equipment. They could be different. Some of them are exactly the same, but make sure you're on the right model number when you're checking these things out. Just put this in here to tell you on a multi-zone unit, this is just a reminder for me, on a multi-zone unit, when you're starting them up, it's easy to get them cross-wired because you get all those wires from inside going outside. It's good if you would tape the wires or wire tie the wires to the line set when you run them so you don't mix them up. But a good thing to do on day one is when you start up the unit, start them one at a time. Start up unit A and just verify that it's cooling. Then start unit B up, or the second unit, go back to A and shut it off. Then you don't have any time delays. And just verify each one is cooling one at a time. Because if you get them miswired outside, unit A is going to tell the B linear expansion valve to start flowing refrigerant to the other unit. And on day one, when you start everything up, they'll all be cooling, but the next day you might get a call and say, the living room's warm and the bedroom's cold, or there's frost on the bedroom unit, or something like that. And that usually is miswired. So good practice would be to start them up one at a time. And then check the temperature. This is kind of what we call a rule of thumb. Across the indoor coil should be 20 to 30 degrees temperature drop for cooling, and a temperature rise, and this says drop, but temperature rise of 35 degrees across the coil for heating is right around there is what we would expect to see if it is charged properly. Okay, the outdoor unit, this is the MXZ8B, the ones with the branch box. The outdoor unit here, right in here are all the dip switches, and right under here is this LED display that we're going to talk about right now real briefly. When you first turn the equipment on, these lights light like this, and these are segments. This is segment 1, segment 2, segment 3, 4, etc., as they're labeled here across the top. In this case, it looks like 1111. And I've gotten a number of calls where guys say, I've got an error code of 1111. That probably is normal. This last one is always lit if there's power to it. And then these others this means that the compressor is operated on 1, segment 2. Segment 2, 52C is a relay drive signal telling the compressor to operate. And 3 would be a bypass valve, 21, where is it? Yeah, is a 4-way valve signal. And 4 here is SV1, which is a bypass. That is your bypass or solenoid valve. So this just tells you what's operating in the unit. However, if you take SW1 here, and I'll show you in a second how to change these switches, which are showing down here is O is off and 1 is on. If you turn these on and off different ways, we can make this display read other things. And if it goes into a failure mode or it sends a signal, could take up to 20 minutes for it to throw a signal. So a good idea is when you first get to one of these is to open up the panel and look at this and see if there is some sort of a display that looks like this. This says 5105. It would be back and forth between like 51, 5105, 51, 5105. 5105 is the error code. 51 is where that error code is. That is the address. And if this outdoor unit here, right up here on these switches, was addressed to 51, that would mean that the error code 5105 was on the outdoor unit. If it was another address, it would be the indoor unit. So what that means is these are if you look it up in the service manual that's available on my link drive, these are your check codes. So 5105 is telling me that that's an outdoor liquid pipe temperature thermistor. TH3 is open or shorted. If you had a thermostat or a controller on the inside, it would be sending this U4 code. And if you look up U4 code, it's going to tell you it's the same as a 5105, and it's this thermistor. So it's telling you to check the thermistor. Now, let's go back one. These are the thermistors. And what did it say? TH3. So it's telling you to check TH3, which is this one right here, which is a white plug. It's telling you that that thermistor is probably bad. Thermistors are, they change resistance as the temperature changes. And so what that will do is, if it's bad, it's either open or shorted. If it's got a resistance to it at all, it's probably okay. And I can show you on the service bulletin that you can actually see what that resistance is at any given temperature. But normally I would unplug this and put your ohm meter across it and look for short or open. Believe it or not, these are very fine wires, and in the outdoor unit, I found them broken many times. Usually it's a rodent, a mouse gets in there and chews on it. So that would tell you what to check, and chances are you will find a broken wire is what you will find, and you need to replace, either repair. If you're going to repair it, make sure you don't just twist it together, because it's just a trickle voltage that goes through there. So you have to make sure you have a very good connection. You could twist it together and solder it, would be the best. Better yet would be to replace the whole thing. Those butt crimp connectors do work, but then you have to tape it off, make sure it doesn't touch anything. Now the other thing on this display, that if you change dip switch SW1, if it's all off, which is the way it is from the factory, you're going to get that segmented displays showing 52C and all, like we just showed, and 8 being always lit. This last one always lit. But if you change these dip switches, this display can actually give you a reading. It'll actually tell you what's going on. So if I go down here to let me keep looking here. Come down here to TH3. I think it's right here someplace. Can't see it, but if you can find TH3 here and you switch these dip switches to these positions, it will actually tell you, I can't see TH3. It's got to be right in front of me here. Maybe it's on another page. Oh, right here, TH3. Number 78 is TH3. So if I turn switch 1 off, 2, 3, and 4 on, and the last from the right on, it'll actually display on that little segmented display the actual temperature it's seeing. If it sees a negative 99.9 or a 999.9, it's shorted or open. If otherwise, you can actually read the thermistor temperature right on that display. And you can see on here, you can see the LED opening, how many pulses it's opened, what the high pressure temperature sensor coming off that compressor is reading. There is literally 253 options here that you can look at. So it even gives you your target superheat if you switch those switches in the right position. It's 4:30. It's probably a good time to quit. Looks like I've lost, no, I still have some other people here on, so I'll go for a few more minutes here. When you open up the top of some of our units, you look at this circuit board and it's upside down. But in the service manual, there's test point diagrams that actually show the underside of the circuit board so that you can actually say that if I go between this point here and this point here, I should be getting 12 volts DC. If I go between here and here, I should be getting 5 volts DC. You can actually look at the thermistor and everything from the top side. So you can do a lot of your testing from the back side here without having to lay on your back and look up or try to get the circuit board out of there. So that makes it a little easier. Here's a thermistor chart. There are different thermistor charts, so make sure you get the right one. This one happens to be for an RT62, and it's telling me that this is resistance. So at 400K ohms, I should be seeing 50 degrees. So if it was 50 degrees outside, I should be at 400K. At 100K, I should be somewhere between 104 and 122 degrees. So you can check out the thermistors and see if they're working. The LEVs are basically, the red wire here connects is a common wire, so you can check between red and white, red and orange, red and yellow, and red and blue, and you should be at this sort of ohms. The difference between this and this is at 14 degrees, you're going to be at 37 ohms. At 104 degrees, you'll be at 53 or 54 ohms. So as long as you're between there, you should be fine. The LEV little motor on the top should be fine. And the high pressure switches, these are what they open. You can see here we open at about 700 pounds and close at 537 pounds. This is a test diagram. This is not to help you charge the system. This is just based to see if it's working properly. If you throw the system into test run or emergency mode operation, on a P series, the test run will be a dip switch on the outside. On an M series, it's a button on the indoor unit. It's an EO switch. It's an EO SW. It's an emergency operation switch. You throw it into the emergency operation or test mode and make sure the fan is on high. That fixes the compressor speed at one particular speed. And in this case, this is your condensing pressures at the outdoor given temperature. And this is your suction pressure at an outdoor given temperature. So if it's 80 degrees and you're reading 130 pounds of suction and it's 75 degrees inside, it's performing just fine. This is, again, not intended for charging. It's just to see that the system is operating properly. If you aren't operating properly, make sure the coil is clean. If you think you have a leak, look for the leaks. If you do have a leak, remove the refrigerant and recharge by weighing in the charge. This is another code for drain sensor abnormality. And it's in there, if you do run into something like that, there's also these ladder diagrams that will walk you through, is it working correctly, yes or no, and move you right through and help you pinpoint any types of faults in the system. And you can always call us at any time too, and we can help you. Primary errors show up as the blinking LED light or the display on the outdoor unit. In the system, it talks about inferior phenomena. What that is indicators that won't show up on an LCD display or a blinking light. There's something that you will have to find on your own. You listen. Is something making a terrible noise like the compressor, or is the fan hitting something? Is the fan running? There's no lights on at all, so you open up the unit and you smell something burnt and find out that the main board is burnt up. That's something you're going to have to find on your own. And obviously, if there's no power to the unit, you're not going to get any kind of an error code. So the instructions refer to inferior phenomenon, and that's Japanese speak that's been translated. And just be aware that if you see that, it's something that you're going to have to look for, listen for, smell, and it should kind of show itself that it's something that did not throw a fault code. like killing power to the unit won't throw the fault code. So if you blow a fuse, you're going to have to find that on your own. It won't give you a code for that. P-series error codes show up like this on the controls. It'll be like a P4 or like a 5701 would show up, or a P5. That's the type of codes. You go look it up and it tells you here P5 is a drain overflow protection, and you'll have to find out if the drain is plugged or if the float switch is bad. Kind of walks you through what to look for and how to fix it. Pretty simple, makes it pretty easy. On the P series, this is an MA controller. This one was a PAR 33, which we still have, and we're into transitioning over to a PAR 40. The only difference is instead of these little symbols on the bottom, they changed it to an actual English speaking. That means menu, that means return, that is select, and this means power. It's the only difference. But on either one of these controls, they look exactly alike. And this would be your error code would show up as an E4 error code unit, indoor unit. It'd be an OU or an IU, outdoor unit, indoor unit. So it kind of tells you where to go. This stat, you can also, there'll also be a blinking light down here, and you can plug in your phone number, that if there's an error code, they'll know who to call. This also has some test run and some function settings. You can go in there and see what the voltages are, what the temperatures are. You can see that all through going through the menu. So this particular control kind of helps you do some troubleshooting as well. You can change things like static pressure and all on the indoor units by changing the setting numbers through this particular stat. Makes it kind of nice, kind of easy. There's a service menu and a password to get into the service menu. The password is in the book if you look, but the book is like half an inch thick. It's 9999. We call that the angry German, 9999. That would be the maintenance or service password to get into it. Again, we talked about this, checking out the compressor. And all of this information is available to you on MyLink Drive. Everything you need to know about this equipment is on MyLink Drive. And just wanted to make sure if I got anything else here we need to talk about. Not really. That is pretty much the end of the presentation. We normally do in Utah and in Plymouth, Minnesota, Minneapolis, Minnesota, and we're building a training center in Milwaukee as well. We normally do a 2-day hands-on type class, which is a not quite so fast, a little easier, more data. But unfortunately, all the hands-on training is off right now. So in February, we're going to do some training that will be remote for day 1 and hands-on day 2 will be in the facilities, but they will be limited to the number of people. So if you've got any questions, you can unmute your mic right now and ask questions, or just email me at bill.snyder@galarson.com, or you can call and ask any of our service advisors at 800-827-9508 and just hit option 2. So if you have no questions right now, we are done for the day. So you guys have a good day, and thank you for watching.